Dia nggak angkat teleponnya. Tapi kelihatannya mungkin diperhatikan, tapi barangkali sibuk beliau.
Oh iya, mungkin
Kalau misalnya kita mulai saja, nanti kalau akhirnya datang, nanti bisa selesai acara baru dia menyampaikan speech kan bisa.
Oh iya, baik Prof.
Bagaimana Dinda, Pak Akbar?
Ya, mungkin kita mulai saja, Prof.
Ya,
Untuk
karena sudah ada pembicaranya kan?
Ya, baik, baik, Prof. Okay. So we will start the webinar. Okay, wait.
Should we start the webinar?
Yeah, I think Prof. Nicole, we are ready to proceed with the webinar, right? Okay.
Okay.
Okay. So, yang jadi, okay. So.
Yes. Okay, all right. Ladies and gentlemen, as we are about to begin, please your attention. I have a note to make before we begin today's webinar. I would like to seek your cooperation in completing this webinar. Kindly switch your microphone to silent mode or mute to avoid interruptions. Thank you for your kind cooperative and attention. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon, everyone. The Honorable Dean of Grade School, Universitas Hasanuddin, Prof. Dr. Budu, PhD, SPM, QM, Med 8, and the Honorable Prof. Dr. Engineering Adi Maulana, STM Field, as the Vice Rector of Partnership, Innovation, Entrepreneurship, and Business of Universitas Hasanuddin. And importantly, in this beautiful moment, I would like to welcome Professor Nicole from University of Birmingham, United Kingdom. Good afternoon, Professor.
Good afternoon, everybody.
Yes, she will be the speaker at our event today, and respectable all participants of this seminar. First of all, let's thank the Almighty Allah Subhanahu wa Ta'ala, who has given us mercies and blessings so that we can attend this agenda without any troubles and obstacles. Secondly, salawat and salam may always be given to our Prophet Muhammad SAW, who has guided us from the darkness to the lightness. And I would like to introduce myself. I, Israini Wilanda Iskandar, will be your master ceremony this morning. Welcome to today's Top Scientist webinar series with title Buried Infrastructure Monitoring, S16 and New Sensing Technologies. And we would like to thank everyone here for making time to attend this remarkable webinar. Distinguished guests, ladies and gentlemen, let's open this webinar by reciting Basmalah. Bismillahirrahmanirrahim. And on this occasion, allow me to introduce you today's agenda. The first is the welcoming speech by Dean of Grad School, Universitas Hasanuddin. The second is opening speech by Vice Rector of Partnership, Innovation, Entrepreneurship, and Business of Universitas Hasanuddin. The third is the core of webinar with title Buried Infrastructure Monitoring S16 and New Sensing Technologies by Professor Nicole Meje. Continue with the discussion session. And the fourth is the closing and photo session together. All right, the first agenda will be a welcoming speech. Please allow us to invite Prof. Dr. Budu, PhD, PM, QM, Med 8, Dean of Graduate School, Universitas Hasanuddin, to deliver his welcome remark. Please welcome Prof. Budu.
Thank you, Isani. To the Honorable of our guest lecturers from University of Birmingham, United Kingdom, Professor Nicole Meche. Good afternoon, Prof. Nicole.
Good afternoon.
Yeah, thank you very much for your opportunity to join our webinar and to be a lecture today. And all of the colleagues and students from Hasan University and outside of our institution who attending this webinar. On behalf of Graduate School of Hasan University, we would like to thank you, especially for Professor Nicole Meche, for taking the time out of her busy schedule to participate in this webinar. We would like to virtually welcome to you And once again, thank you very much for your coming to Graduate School Hasan University webinar in virtually program. The Graduate School in Hasan University is a faculty of multidisciplinary postgraduate program from various academic disciplines, ranging from science, technology, engineering, mathematics, medical science to social science. We believe that Prof. Nicole's lectures will be perfectly aligned with the issues and challenges that we face not only as academic or researchers, but also a civilization in general. We think that the topic for today's lectures is Barrows infrastructure monitoring, existing and new sensing technology. Reading from the topic, this is a very interesting topic instead of monitoring Barrows infrastructure and the technology involved. Although I am not an engineer, I am medical from Nicole. I believe the principle are probably the same in medical field. The less invasive the monitoring scheme, the better. It means that if we can monitor patients' health without invasive procedures, we can also monitor the various infrastructure without digging up the ground. We hope that these lectures broadens the perspective of our lectures and students on infrastructure monitoring and inspires them to deepen their knowledge and conduct research on the subject. For the lecturer and students, we highly encourage you to proactively participate in question and answer session, asking any question you have to Professor Nicole. And we would like deeply to thank Prof. Nicole to respond the question from of our lecturer and student when they release their question today. Before I end my speech, I would like to quote a very interesting Chinese folks. He who asks a question is a fool for 5 minutes. He who doesn't ask a question remains a fool forever. So we hope you can learn much from this webinar. That concludes my welcome speech, and I wish all participants best of luck with this webinar. Thank you very much. Let's rejoin the webinar. Assalamualaikum warahmatullahi wabarakatuh and good afternoon.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Prof. Dr. Budu, for your delightful speech. And next agenda will be an opening speech. Allow us to invite Prof. Dr. Engineering Adi Maulana, STM Field, as the Vice Rector of Partnership, Innovation, Entrepreneurship, and Business of Universitas Hasanuddin to deliver his opening remark. Please welcome Prof. Adi.
Okay, thank you, moderator. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. A very good afternoon, everyone. First of all, I would like to say thank you to the organizing committee, our respected Dean of Graduate School of Hasanuddin University, Professor Budu, and then our respected speaker for today, Professor Nicole Meche. Thank you for your time to share your knowledge in our Top Scientist webinar series. Okay, I am very happy today because as I can see from the flyers that the topic of the webinar series today is buried infrastructure monitoring, existing and new sensing technology. Well, if Professor Budu has already mentioned that he's coming from medical science, I'm from engineering science actually. So I'm very interesting, honestly speaking, in this topic. And then my field of expertise is also in disaster management. So of course, I will be very interesting to have the material of Professor Nicole today. And then once again, I would like to extend my appreciations to the organizing committee, especially to Graduate School of Hasanuddin University. I know that Graduate School of Hasanuddin University is one of the school in Hasanuddin University who is very productive to help to conduct this kind of webinar series. And then once again, also I would like to say that this Top Scientist webinar series actually one of our program in World Class University program. As we know that Hasanuddin University is really committed to become one of the world-class university in Indonesia, and then we really happy, and then we are very happy to have this kind of webinar series. So our students, not only our students actually, but also our lecture can get some more new information. The moderator asked me to formally open this Top Scientist webinar series on behalf of Rector of Hasanuddin University. Let me open this Top Scientist webinar series. Once again, thank you, Professor Nicole Meche. And then for all participants, I wish we will have a fruitful discussion, and then we can get many more information from Professor Nicole Meche. Thank you very much, and then yeah, wish the best of webinar series. Thank you.
Thank you very much, Prof. Adi Maulana, for your delightful speech. And ladies and gentlemen, now we proceed to the webinar agenda. This presentation will be delivered by Professor Nicole Meche, and also this agenda will be guided by Mr. Muhammad Akbar Walena, ST MSc PhD, as the moderator. We invite you all, the distinguished speaker and the moderator, to come to the screen. Please, time is yours.
Okay, wait a second. Yeah. So thank you very much for the opportunity. So before we invite our guest lecturer today, I would like to give a brief introduction of our speaker today, as well as a short summary regarding our topic today. So Nicole Meche is a professor of infrastructure monitoring and head of enterprise engagement and impact within the School of Engineering at the University of Birmingham, United Kingdom. She's also the director for sensors of the National Buried Infrastructure Facility, part of the UK Collaboratorium for Research on Infrastructure and Cities. Professor Meche leads the geophysics, geophysics research of the Birmingham Large Quantum Technologies Hub for sensors and timing. Prof. Nicole works closely with the industry through 12 jointly funded research projects, developing sensors and novel processing methods. Prof. Nicole also a member of the Chartered Institution of Civil Engineering Surveyors and the American Society of Civil Engineers. She leads the UK's contribution to the ASCE utility standards and the US Transportation Research Board utility committees. So in regards to the topic today, which titled Buried Infrastructure Monitoring, Existing and New Sensing Technologies. So buried infrastructure carrying water, gas, electricity, or broadband is essential for everyday life. However, the location of these pipes and cables and their condition is often poorly understood, which has a significant implication on both the performance and asset management. So the lecture from Prof. Nicole will cover a range of existing and novel sensing technologies which can locate and measure the condition of these assets without the need for any excavation. So without further ado, I would like to invite our guest lecturer, Prof. Nicole Meche. Time is yours.
Thank you very much for this introduction, and thank you also for the organizing committee, the Dean and the Vice Rector, for allowing me to speak today to everybody. I hope it'll be an interesting presentation and everybody gets something out of it. There is actually a bit of synergy between infrastructure, buried infrastructure, and the sort of healthcare monitoring. So I will refer to that at times. So we've already heard on a number of occasions what the title is, but before I go into detail on the technical side, I'll give you a bit more background about myself and sort of my career. So I am a civil engineer. I did my degree at Hanover University in Germany. I graduated in 1998. I then got a PhD from Birmingham in 2002. That was actually in the field of coastal engineering, interesting enough, so looking at erosion processes along the coastline. I then worked as a postdoc until 2008, still everything is at Birmingham, and I've been an academic since 2008. I got promoted to professor in 2018 and have been the head of enterprise engagement and impact since 2020. So we're really driving, so the ambition of Birmingham is to really make sure that we make impact from our research. And I've got the privilege of heading this up for the School of Engineering. Since the beginning of this year, I've also become the director of our National Buried Infrastructure Facility. You see me standing in our facility on that picture, but there'll be a few more images later on, because I do think that there might be potential for future collaboration in this area as well, having this facility. I do have to say a few words about Birmingham as well, just in case you don't know where Birmingham is or you have not been to Birmingham. So Birmingham University, so Birmingham is in the sort of centre of the UK. It's called the West Midlands. As it so happened today, the Commonwealth Games have started last night. So the university is actually hosting the hockey and the squash. So I'm hoping to actually see a few fantastic sports people and watch some of the hockey later next week. But from an academic viewpoint, we are ranked top 100 of the world's university and top 20 in all the UK universities. We are really, Birmingham is the second most targeted university in the UK by top employers. So employers come to us. One thing I should say, Birmingham is a civic university. That means we don't specialize in a specific area of teaching or research. We have a very broad range, and we probably do everything. We teach everything at the university other than veterinary. We don't do veterinary. And I think there's one other we don't do, but otherwise we do all the science, engineering, but we also do the medical. So we've got a medical school, a dentistry school, but we also teach all the law, social science, languages, business, and so on. As you can see, it's quite a large university. We've got 34,000 students at undergraduate and postgraduate levels. We have 11 alumni and staff who are Nobel Prize winners. And the university is actually investing significant amount of money. So those of you who may have been to the university a few years ago will, if you come again now, you will actually see some significant change. So that's actually really good, because there's really a vibrant feel at the university, because there's more investments, new buildings going up. I'm sitting in a brand new building in engineering that opened only last year, and I've already shown you a picture, a very short picture of my laboratory, which also only opened last year. Coming a bit back to the economic impact and what Birmingham University does. One of the things, if you don't focus on the text, but actually focus on the picture, you actually see some of the university in the background. One of the most famous thing is the freestanding clock tower, the tallest clock tower in the world. There's also a interesting fact is that you can get 2 double-decker bus around the clock face itself. So it is really quite big. You might also see a lot of it is sort of red brick. So it is known as a red brick university. So it is a campus university, so it's actually really quite nice. So it's not scattered around the city, it's a campus university. And more recently, we've developed a sort of a green heart area, which you can just about see in the picture. So it's here, really open space. But from an economic impact, it shows you, if you look at the text, the importance of the university for the local region, as well as the UK PLC in general. So the university contributes 3.5 billion every year to the economy. Almost 1 in 50 jobs depend on the university in Birmingham. What's quite interesting is that nearly half our graduates stay in the local area. So there's lots of opportunities in the local area. And as I've already said, we're really driving innovation, working with businesses of all sizes. But we are also a global university. So we've got a campus in Dubai. Again, that's what you see in the background on the picture. So that opened in 2022. Initially, it's focusing on engineering and business, but we're expanding this. So this is a brand new campus. Clearly, we're collaborating worldwide, so not just in Dubai. Also, we collaborate with over 4,700 institutions. And one of the things that we are quite proud of is that a lot of our publications, over 50% of our publications, are with our international collaborators. So that shows that we're not just insulated internally, but we're actually a broad university, international university. Finally, in terms of some of the university firsts, so the university I've already mentioned is a civic university, welcoming students from all backgrounds. It, interesting enough, it actually runs a secondary school. So that means students or pupils from 11 years onwards go to our university school. We have got the Dubai campus. We were the first university to develop to incorporate the medical school. And we also have a college. We run a college, which is the National College for Advanced Transportation and Infrastructure. So it is in my area. So really, we're offering education from ages 11 all the way to PhD. And that's actually quite relevant. So we're really trying to enable students to consider university. So that's our secondary school. But we're also saying it doesn't have to be a university degree for everybody. Apprenticeships and routes through that area, through our college, is also something we want to promote. But what we're really doing is working very closely across that spectrum to really ensure everybody has an opportunity to benefit from the knowledge and experience at the university, but also we can promote people's careers through different routes. A bit about the School of Engineering. So the School of Engineering has 3 departments. I'm in the Department of Civil Engineering, but we also have electronic, electrical and systems engineering, as well as mechanical engineering. But it's all one school. And we that was formed in 2016, and that was a deliberate move because we realized in practice, we can't work in isolation. We have to work in collaboration. And it's much easier if we're collaborating across one school. So this is my final slide before I go into my actual technical talk, just to give you a bit of again, a few more ideas about what the School of Engineering is like. So we've got 1,800 undergraduate students, 400 postgraduate taught students, and 300 PhD students. So you can see there are quite a large number of students in engineering. We probably have a research income of around 15 million every year. We currently have around 100 academic staff, but we keep expanding because we're increasing our student numbers, and that means we need more staff. We've got about 80 research staff, and there are there's a lot of the ranking that we're really proud of. So we've got quite a few notable ranking positions in different surveys. But finally, coming over to my actual talk. So I start off with the problem space. And really try to explain what I'm interested in, because not everybody might appreciate what it looks if it looks below the ground surface. Then I talk about a project we did a few years ago called Smart Pipes, where we looked at using existing sensors in a completely different way. We then did something called Find It, which was quite a clever play on the acronym, but again, it was finding buried infrastructure. But it's not just the infrastructure itself, it's also trying to understand the ground. And I'll finish off with some examples on the quantum technology sensors that I'm involved with. But let me first start with what the subsurface looks like. If you go back to 1500, Leonardo da Vinci said that we know more about the stars above us than we know about the ground below us. This is still true today. That hasn't changed. So we are 500 years on, and this hasn't changed. We still know more about the space, cosmos, than we do what's below our ground. And I'm one of these people who tends to take pictures every time there's an excavation. And these are some of the pictures that I've taken over the years. And this is just focusing on pipes, and my research is much broader, looking at other things that are in the ground. But if you look at the pipes that are below there, you can start to appreciate how complex this is. So if we go back to the medical analogy, none of these pictures show keyhole surgery. They actually all show really invasive surgery, i.e. we're opening the ground. The problem with this is that you're actually incurring quite a lot of problems at the ground surface, because what it generally means is that these pipes and cables are laid in the street. So you have to close your roads, you have traffic jams, you have congestion, you have cars driving down roads that they're not really designed for and causing secondary problems. Well, one of the big challenges you find is how complex it actually is in the ground. So if you look at this picture here, this is taken in Birmingham near New Street Station, so one of our main stations. And you can see how many different assets are in the ground. Most of these blue ones are water pipes. These are cable conduits, so they have broadband or electricity in. But you can see it's not a straight linear asset. It's all different angles. But what you can also possibly see is that it's different materials. So here you see what's called polyethylene, so a plastic. There's a plastic here, but in between here is our cast iron. So pipes we lay at the moment are made out of polyethylene plastic, but previously we have had ductile and cast iron in the ground. And there are still examples of that. So just the complexity is one problem. So if you know where, if you open a chamber and you see where the pipe is, you open the next chamber, you cannot assume that the pipes connect in a straight line. So that's one of the problems. The other problem is the damage that we're doing both to the ducts as well as the pipes. So the middle pictures, this one shows a bit of damage, maybe not as bad, but it's clearly going to get worse. But it also shows that it's a bit offset here. This is a bit worse. There's a much bigger offset here and it's basically broken. And this is because somebody probably damaged it during excavation. And the problem with that is that we are currently in the UK rolling out a lot of our broadband fibers. And the way broadband fibers are rolled out is they are blown into the conduit, into the duct. But you can't do this if you've got this offset. You can't just blow the fiber down. So that means you have to do that excavation like they've done here. You have to repair it, close it up again, then try and put your fiber in. But that can be quite complicated. And the Find It project specifically focused on exactly that. The other problem you see here, this is actually a gas pipe. So this is actually quite scary. This is a gas pipe, but you also see the surface here. This is the pavement. So you see how shallow the gas pipe is buried here. So that means if you do any excavation, you really have to know very accurately where your buried assets are, because otherwise the risk of damage is significant. And it actually, in the UK, unfortunately, we know that around 5 to 6 people lose their lives or are seriously injured every year because they damage or hit a buried asset. So that's a really sad fact, and we really want to avoid that going forwards. But you can also see these cables are electricity cables. So this is gas. So you don't really want those close to each other. So you can see how in practice, this is not how it was designed, but in practice, people actually lay it. There's just a bit of a brick, a bit of wood to just separate those out as much as possible. As I said, clearly not a good way. You can also see that here are some more conduits that are just broken off when that excavation happened. So I'm one of these people, wherever I am, in what country I am, I'd take pictures of holes. That might not be a good fact about me, but that's what I do because I want to see whether it's different in other countries. And I'm sure maybe you can send me some pictures of what it's like in Indonesia for some of the excavations. But coming back to my pipes or so this is a district heating pipe. It doesn't actually matter what it is, but most of our pipes are in the ground. Even the newer pipes we lay, they don't have any sensors on it. We call them a dumb pipe. So they don't tell you anything about how they behave, where they are. Most of our pipes in the UK are actually 100+ years old. And this is where we are now starting to struggle with the sort of condition management and trying to look after them. So one of the projects we did is we said, what we really need, we need to have sensors on this because we need to be able to monitor the performance of our buried infrastructure, ideally from the surface without having to excavate, because then we can make our assets last maybe much longer, or we can intervene much more proactively before any severe damage happens. So we said what we need to add sensors and we need to add communication. So the principle of what we came up with is that we have our pipe in the ground. We've got our sensor nodes. So these are our sensor nodes and they can communicate with each other, but they also communicate to a master node, which is probably also in the ground or just above the surface. And that then communicates to a cloud and then can send you information out. And the key thing is, the key idea was that if these can communicate with each other, we can we only send the information to the master node if a change happens. So if everything is in the sort of green zone, we don't even inform anybody that there may be a problem. We record the data, but we don't pass the data on. So that was the theory. So what did we do in practice? So in practice, we developed something, but we had a few requirements. So we wanted a sensor that was non-intrusive to the pipe structure. So what we mean by this, if you've ever seen, for example, a pressure sensor is a tapping, you actually screw it into the pipe. So that damages the structure of the pipe. So we said we don't want that. We needed something that has enough accuracy. We needed something that was simple from a signal processing viewpoint, which had a wide range in terms of communication, but also was low cost. Because one of the challenges we have in the UK is that water is cheap. That may change with climate change now. So this may all change in the future. But at the moment, water is cheap. I mean, gas is no longer that cheap, but certainly water is cheap. So if you add sensors and they cost hundreds of pounds or hundreds of dollars, it adds a significant cost to the supply of your water, and water companies wouldn't want this. So what we basically found out is you can have a force sensitive resistor or FSR sensor. So the blue one is our pipe. That has pressure because you've got pressurized water in the pipe. You have a sensor and you have a clip on the outside. So the sensor was very simple. This is what the sensor looked like. It has an area here, which basically has a layer and a spacer, so a conductor. So when it presses down, it connects your conductors and you have got some electric current running through, and you can measure this electric current. So in practice, this looked something like this. This was in the laboratory. So we had a so-called Jubilee clip, so just a strap around the pipe, and we had a sensor just underneath here. So this bit is the sensing area, not the bit that you see at the back. So that was the principle. So really cheap, these FSR sensors cost less than $1, and we didn't need to do any tapping. The only challenge is that you need to reach the whole circumference of the pipe, but we looked at alternative solutions for that as well. So one thing we did is we didn't just do it in the laboratory, we actually also did it in the field. The one thing we didn't practice or try in the field, and it's still proving a bit challenging, is that we still had a cable. We still had cable connections. In an ideal world, we want this wireless. So we worked with one of our water companies, and in this case, we actually did a bit more for keyhole surgery. So I don't know whether anybody has seen this, but this is a vacuum excavator, which basically sucks the soil up into its drum, and otherwise it can give either takes the soil away or it most likely puts it back in the opening. So here you can see the pipe, and you can just about see the cable clips. As you can see, you've got water because it's quite wet in the UK, so you've got the cable clips here attached. So one of the key things is, so we had our pressure sensor, but we also had some temperature sensor, one very close to the pressure sensor, so on the pipe, and one further in the ground. We also actually had some vertically in the ground as well. So what this shows, this is a slightly complicated figure, but I'll try and explain this. So on the x-axis here is time. On the y-axis here is temperature, and this is the FSR output. There's just a digital output. Don't worry about the units. It's just literally what comes out of the digital converter. So it doesn't simulate a pressure or anything like that, or not a pressure as in it's not converted to pressure. That's what I'm trying to say. So what you can see here, so the green one is the sensor that was 30 centimeters away from the pipe. So the green one is this one. And the red one is the one that's on the pipe itself. And here you've got your pressure sensor, and you can see it's quite noisy, but it has these sort of drops every now and then. And the idea was that we could relate our pressure drops whenever there was a change, an abnormal change in temperature. So you can see there's a temperature change, and this occurs because when you have a leak, the water rushes through and you get different temperature water in the pipe. That's why you get a slight temperature change. And the idea was that we could combine the temperature change. So whenever we had a temperature change as well as a pressure drop, those were the times when there was a leak. So we induced a leak into the system, and we could measure this. And this was actually really successful because these points do actually show at times when we induced the leak. So whenever there was an abnormal pressure change, which also coincided with a pressure drop, that's when the leak was that we induced. So therefore, that gave us confidence that this system worked. So as part of this project, we actually ended up doing, on the sensing side, we developed this non-invasive relative pressure sensor. So it doesn't measure absolute pressure. So if you want the actual pressure in the pipe, you still need a pressure tapping. We also developed a sort of a node design. We looked at an installation. So the Jubilee clip idea is really cheap, but we ultimately also looked at a clamp that we can put on the surface. So we can go in with keyhole surgery. So we literally just have a hole rather than a trench. But it was really reliable, and it was cheap, and it was scalable. Obviously, in the talk, I don't have enough time to go into a lot of details. So this is just a summary. And if anybody's interested, I can share these. This is just a summary of the various papers that we published based on this project. So this paper, our last one in 2018, is really the summary of our field trials. So if you're interested in the field trials, that's really a good one. Some of the sensors and actuator ones are looking more at the design of the system, but also how we can communicate through the ground. One of the idea we actually had, rather than having something on the outside, is also whether we can actually include something in microchips or nano sensors into the pipe material itself. There's a paper here, and there are more than that one. And this is our first concept paper that we did now 11 years ago. Most of these are open access, but if you're interested, as I said, I can hand them out. I can share them. So coming to the next project, which was Find It. So that's something that we did with industry. So that was together with British Telecom, or BT, as well as RSK and Geomatrix. So this shows that we're really looking at sort of industry problems and trying to do industry, address industry challenges. I've already mentioned that in the UK, we're rolling out broadband communication. So they're putting fibers in, getting rid of the copper cables. But the way they do it, they open an access chamber and they see the conduit, and they try to blow it in with air, blowing the fibers. And that only works if there's no blockage in the conduit or there's no offset in the conduit. So the question was whether geophysical sensors from the surface can help find any blockages or any offsets, so that you can address this before you get on site and before you try and put your cables in, your broadband fibers in. So I'll show you this video because I think it actually gives you quite a good impression of what this was all about. So this is focusing in on our test site at BT. One of the things we did a laser scan of the area. So we have a good digital terrain model. And this is just standard geophysical equipment that we used to collect data of what's actually in the ground, because even though this is a test site owned by the company we're working with, that doesn't mean that they know exactly where their buried assets are. So one of the sensing technologies we looked at was ground penetrating radar. You can see it move up and down. It's obviously a time lapse, so my colleagues don't move that fast. Here are some of the results, and you can actually see how difficult it is, but these are animated time slices, so they go through the different depth layers, and you can start seeing at different depths that some pipes appear. So there's a pipe. There was one earlier which went along here, which you can just about still see. That's all the services that ground penetrating radar detected. We then did some CCTV, because one of the things we were interested is to look at blockages, because this was our test site. So we needed to know what the status quo was, so that we can benchmark. So basically the ground truth, so we can benchmark against it. So this is a typical CCTV image. I have to say these are very clean pipes. This is not the quality of image you sometimes get, but you can see that there's a partial blockage detected here by the CCTV camera. So one of the things we then did is we used the site itself and looked at some blockages, but being in academia, we want to really have control of over our tests. So one of the things we did, we actually installed our own test site. So we had a total of 5 ducts with different defects. So one of the defect was we had an empty pipe, but we have mobile partial blockages, and I explain what that is on the next slide. One, we had some holes drilled in, one open holes, ones we sort of taped up, because if you have clay surrounding, it can actually feel as if you have a clay pipe, even if your main pipe is damaged. We looked at breakages, something like this, whether we can detect this. We looked at changes in material, so from plastic to metal. And we also looked at changes in depth as well. So I should say the conduits are quite shallow in the UK. They're around 300 millimeters. These were our partial blockages. So we literally had cylinders filled with soil of different diameter. If this was our pipe, we literally dragged our soil cylinder through the pipe, and that simulated different blockages at different positions. So these were up to 60% blocked, and the idea was still, can we detect them from the surface? So one of the things we did ground penetrating radar at the surface. And this was an example where we had a blockage, and we could detect, so you can see here, you've got a change in, it's maybe not that clear. So these are typical ground penetrating radar images. Oh, this is a typical ground penetrating radar image. And it is quite difficult to maybe interpret. So this is going along the pipe. So normally you do a lot going across the pipe when you want to detect the location. But in this case, we wanted to detect the defect. And if you're actually looking at the data behind the image, you can see that the amplitude of this data is a lot less than the amplitude of this data. So we can actually, if you understand this, and if you do your post-processing accordingly, you can actually use ground penetrating radar to detect blockages. As it says, this was 100% blockage. So the question was, could we also detect smaller blockages? We then did a bit more simulated data, whether we can detect a smaller blockage. And what you can see is you probably don't see much in the image itself, the GPR hyperbola, which is your typical image that you get. But when you look at the data behind this image, you can see a change in amplitude. But really, it is quite a subtle change. And if you have a lot of noise and there's a lot of variation in the ground, that can actually that can manifest itself in similar results, and therefore you may not be able to detect these smaller blockages. We then looked at an empty duct, and we can easily detect the empty duct, interesting enough. So I've got a colleague who's very good at graphics. So we did have a mole hole. So we had a mole coming up. So you can actually detect that there's a path that the mole has dug. You can see that in your ground penetrating radar. It's not what we wanted to see, but that's what we could see. We did this at different times in the year because we have different water content in the ground. And I'll explain why that's important a few slides later. We then also did some of the acoustic tests. So the acoustic tests work slightly differently. So you do need to have access to the end of the duct through a chamber, but you still don't need to excavate. You just need to get to the end of the duct. As you can see, this is clearly not a industry prototype. This is a research prototype. You can see all the cables, but it's nothing really different to a speaker that we put at the end of the duct, a clever speaker and a clever sort of also microphone, and we listen to the return signal. We did this for quite a number of pipes. We also had quite a long one. This was at the surface to a certain degree for the proof of concept test. It doesn't actually matter whether it's in the ground or above the surface. What you can see here, you can see quite a lot of connections here as well. And the question is, what can we detect when we do our acoustic survey? We had a bend as well. So again, there's a lot more in the technology that, again, I don't have time in this talk today, but you can see that you can detect the ducts joints, so where it's joints, so you can see this in your reflected signal. And you can also see the end of the pipe as well. But this is just indicating that on this occasion, there was no blockage. We have another one where we know where the end of the duct is. We've done multiple sweeps, and we can actually see areas where blockages are because the signal looks very different. So this was a clear indication that acoustics could help. So the idea still is, if you go in before you try to put in your fiber and you understand the underground environment much better, you can either do repairs before you try to put in your fibers, or you know whether there is an issue. And this has a real advantage because you can plan your jobs much better. The way it currently happens is somebody comes on site, wants to blow the fiber in. If they can't blow it in and there's an issue, they go away from the site, they call a different team in, the team repairs it, repairs one area, they go back, try it again. If there's another bit that's blocked, same situation, the person or the team that tries to block it to blow in the fiber goes away, brings in another team to repair. And that takes a lot longer, causes a lot more congestion on the ground surface, has a lot more impact on everybody driving around generally. So to just summarize what we found, so we've got the in-duct acoustics and our ground penetrating radar. In terms of locating the duct, you can do that with ground penetrating radar. This is something that industry does day in, day out. In terms of partial blockages, we can certainly see that with the in-duct acoustics, but we're struggling with the ground penetrating radar. If we have a full blockage, we can see it with both. If we have multiple full blockages. So you have a stretch of pipe and you've got multiple blockages. We struggle beyond 2 in terms of our acoustics, but we can see it from the ground penetrating radar. If there's what's called cable congestion, so if you've got different cables in it and you don't quite know how much more space is in your conduit, we again struggle with either sensing technology. If we look at where there's water in the ducts, because that's also important, we can do that with the ground penetrating radar. If we are looking at leakage, and this is mainly for water pipes, so this was a bit of a site analysis, you can do that with ground penetrating radar. But what this shows, and there are a few images later, is that it's a sensing combination that's actually really interesting and useful, and it's not a single sensing technology that addresses your challenges. Again, we've got a paper out, which is an open access paper, if you want to read more about this particular project. Just going into how most geophysical sensing technologies work that I've just been talking about. So this is this idea of a ground penetrating radar, and most of it we are sending an active signal through the ground and we're looking at the reflection. The problem is that this electromagnetic signal is affected by the ground itself and is also affected by the condition of the ground, and mainly the water. So if you've got water between your soil particles, that water can actually affect your electromagnetic signal quite dramatically. So that's quite a significant problem. So what's so I think I've said most of this. So it's really a problem because water is a bipolar, so it's a dipole, and you have got the dipole with your electrons on the outside, and the problem is that your electromagnetic signal has also got electrons on the outside and they interfere, which basically means your signal can't penetrate so far in the ground. And this actually means that your ground penetrating radar works different depending on what your ground conditions are. So if you've got, this is symbolizing the summer when I've got low water content, so not a lot of water in the ground, have low attenuation, so my signal strength doesn't get attenuated, I can easily locate a buried utility. If I've got a high water content in the winter, I struggle a lot more and I may not even find my utility. So that's one of the problems. So as a result of this, one of the things we actually need to do is we need to understand much better of what our ground properties are. So water in the ground is really important. So we've done quite a bit of work where we have looked at different soils at different locations. So both more sandy, coarse-grained soils as well as our fine-grained soils. And we've put sensors in, and the sensors that we use are called time domain reflectometer sensors, which you see here, or TDR in short. It basically looks like a fork. So it's a long fork. So this is about 12 centimeters in length, and you poke it, or you prod it into the ground. And what you can do is you can actually see you can measure what's called permittivity, and you can also measure conductivity with the same probe. So again, this is a slightly complicated figure, but what you see again on the x-axis is time. This value here is called ARDP, so it's a permittivity. It's a relative permittivity value. But you can convert this into water content. So your water content is very dependent on this ARDP value. And what you see on this axis is rainfall. So the dark blue values are rainfall. So if it's below 5 or below 0, so below 0, it actually means that my evaporation was bigger than my rainfall. So the water evaporated. If you have it above 0, that means there was rainfall which infiltrated into the ground. All these other different colors, so the red, the green, the turquoise, this blue and the black, are permittivity values at different depths. You can see black is 0.1 meter, dark blue is 0.2 meters, turquoise 0.5, green is 0.8, and red is 1 meter below the ground surface. And what this is really trying to, what we were trying to investigate is what weather condition result in a change in water content in the ground, and how big is the infiltration. So what you can see here, this was a relatively dry period, so there were only a few rainfall events. So a lot of our permittivity, thing, water content was very low. And then we started to have a bit more rainfall, and you can see the ones close to the surface, our 0.1, 0.2 meters, react very quickly. So 0.1 reacts first as a result of rainfall, 0.2 meters as a delay because it takes the time to infiltrate, 0.5 meters an even longer delay, 0.8 meters an even longer delay, and then 1 meter a much longer delay. But you can also see that at the 1 meter here, you don't actually get that much change in your water content. Only when there's a significant amount of rainfall, it then suddenly jumps. So really the idea was twofold. One is, can we use such technology to get this really important factor of water content? The way we would normally do it as a geotechnical engineer, we take a sample and we put it in the oven, we dry it. I see some nodding, so it's quite a tedious process, but it also gives you an instantaneous value, i.e. what it was like at the time you took the sample out of the ground. These sensors can give you that same information, but over a much longer period of time. Again, I've got loads more information on these, so I won't go into that. But so this can be used as a proxy to give you in situ water content as a function of time. But the question is also, can we actually use this to detect leaks? Because what does a leak do? A water leak changes the water content in the ground. So it makes the ground wetter around it. So we use the same sensing technology. This is our simulated small pipe, hose pipe, and we had a leak here. Here are our sensors. We used a range of different sensing technologies. We also did some laboratory tests to calibrate the sensors. We sprung a leak. This is just a trial, just to emphasize this. So we actually did this while there was soil on top of it. And here are some results here. So we can see the leak results in a change in temperature. These different colors are, again, are different depths, so don't worry about it. These are electric properties. So this is your permittivity again. So change in permittivity as a result of the leak, and a change in water content as a result of the leak. So this actually clearly shows that we can detect when a leak starts using this technology. And this is really quite important because leak detection is a really vital aspect. I didn't mention it much about when we did the smart pipes, but water is precious. There isn't enough water in many countries. So having potable drinking water that leaks in the ground and we lose is not acceptable. And our water companies get fined if this happens. So they really want to know where their leaks are so they can go in and fix them. And they don't want to know once the water's at the surface. They want to know before. So finally, looking at the more novel geophysical sensors. So a lot of this was existing geophysical sensors. Apologies, I just need to have a drink. But even though there were existing geophysical sensors, it's not the way industry uses them. So what we found is that there's a lot more information in the data from existing geophysical sensors than we use that industry uses or industry gets out of it. And we can actually work with the data and come up with some clever processing, clever modeling, and support industry to say, you've collected this data already. Did you actually realize you can get this additional information that you can sell to your client? So in terms of our novel sensing novel sensing technologies, it's really quantum. But before I get to the quantum sensor, I just talk about microgravity and the principles, because it's microgravity and it's gravity measurements that we do with our quantum sensor. So one of the issues I've already said is the soil. Different bulk densities potentially causes a problem with with a lot of geophysical sensors that rely on an electromagnetic signal going through the ground. In contrast, microgravity doesn't send an active signal through the ground. So it's not a sensor that you put at the ground surface and you send a signal through. It just measures the acceleration or gravity as a result of the Earth's gravitational field. So what does that mean? We normally have a highly accurate measurement that measures this acceleration. So classical gravimeters rely on a mass on a spring. And if you have a dense material in the ground, think about maybe a concrete foundation or something like this, your mass is attracted by that a lot, not a lot, but attracted by it more. It expands the spring, and we can actually get some information about the acceleration. If you have a void in the ground, could be a tunnel, could be a cavity, could be a big gas pipe. There's air compared to soil. So if you're over the area where there's a void, your mass is attracted less. So you actually have a negative gravitational field. The problem we have with the classical instruments is twofold. One is that spring here, that spring constant, it's very difficult to make them really accurate and make them all the same if you have a number of different instruments. The other thing is, if you've ever used a spring, maybe for structural analysis or so, you know it's affected by temperature. So it can dilate. If it's really hot, it dilates. If it's really cold, it contracts. And therefore, that's problematic if you want to use the instruments over and over again in different weather conditions, climatic temperature conditions mainly. The other thing that's quite challenging is to create test masses that are absolutely identical from one instrument to the next. In terms of interpreting the data, there is a challenge that doesn't matter whether I use a quantum instrument or use a classical instrument, and this is called non-uniqueness. What does this mean? It basically means if I do a gravity measurement, I take an average with depth. So my instrument can't, or my data doesn't differentiate between having something close to the surface that is small or something bigger but further away from the surface. It gives me the same reaction on my sensor. So the interpretation is a lot harder. Here you can see one of my colleagues doing a gravity survey. This is an old gravity instrument called a CG5. We are now at the CG6, and there are pictures later. This is a brownfield site where we wanted to know, where we're working with a company, and they really wanted to know what was the ground below. Were there any features in there? Were there any mine shafts, old mine shafts that weren't on records? One thing you can also see compared to the ground penetrating radar is these are stationary measurements, which means they generally take a lot of time. But why do I do, if it's so challenging, why do I do gravity? Well, sometimes gravity is really the only sensor I can use because my soil is an attenuative medium. So that means electromagnetic signal, the strength will reduce with depth. The problem is that if I think about ground penetrating radar, I sometimes might only penetrate a few centimeters. We also have quite a bit of variation in the ground, which makes it quite difficult with some of the other sensing technologies. And it's often the resolution that is a problem. So what's the smallest object I can resolve with the different sensing technologies? So how does a quantum sensor in contrast work? So it still uses Newton's principle of a falling apple. So we're still looking at that gravitational pull, but it's doing something a bit more clever. It's using the quantum effect. And what does the quantum effect say? It says that a particle, an atom, a molecule can be at two different energy states at the same time. You may have seen, if you've ever typed in quantum mechanics or quantum effect in Google or so, you might have seen a cat that is either alive or dead as a sort of the way it's often symbolized. So this is the same. The atom can be in two different energy stages at the same time. So what do we do in terms of our gravity sensor? We're actually doing something slightly bit more clever because we're using a gradiometer. So we have two atom clouds separated by a certain distance, and we look how these atom clouds behave, and then we take the difference. The advantage of this is that some of the common noise sources, so common vibration, gets suppressed. So if I've got my two atom clouds and they move in the same way, then any common noise sources, when I take the difference, just disappears or is suppressed. And that is a real significant difference to a normal gravimeter, where I have to take into account noise sources. And noise for me is anything that isn't as a result of the signal of interest. So what does this mean? That could be wind. So wind vibrates the ground, causes me problems with my sensor. I do have cars, trains, people walking by, vibrating the ground, causes me issues with my sensor. I have waves breaking on the ocean shore, causes me issues with my sensor. So issues in the way that I measure these vibrations. It's not an issue with the sensor itself, but with the data. So I measure all this additional information, but I don't want this. This is not as a result of my feature of interest. So how does a quantum technology, how does it work? So basically we use a cloud of atoms at each point. For us, these tend to be rubidium atoms. We then, this is our test mass. So the advantage of having rubidium atoms compared to our mass, mechanical mass, is that the mass of our atoms is always identical no matter what sensor we use. We then, rather than using a spring, we use a laser, which has still, if you imagine, you think back of your physics degree, you have a laser, you can represent that as waves. So that again is like a ruler. So what we then do is we take our atoms, we give them a kick, energy kick, and they separate into their different energy stages. So each atom can exist in its different, in either energy stage. We then give it another kick and we bring them back together. At the same time, we observe how those two, in those two different energy stages, how they behave as a result of gravity. So it's all a bit complicated, and I can probably, I've done a whole lecture just on this yesterday, so that would be a whole new lecture. But just to give you a bit of this is a slightly older schematic, but just to show you a bit about what it looks like. So we start off with having our rubidium atoms. We put them in our vacuum chamber because we don't want a lot of kinetic energy. We cool them down so they have really low kinetic energy. We then give them we then, in this case, throw them upwards. Here we give them a kick, they separate into their two different energy stages. We give them another kick, they come back together. And we then use interferometry to measure the changes and ultimately measure gravity or determine gravity. So here you can see the new classical instruments called a CG6. So this is as a gravimeter on its own, but you can also stack it and get a pseudo gradiometer. So this is not the same as the quantum instrument because they are individual instruments and they all have individual issues, but you can still take a measurement from here and a measurement from there and take the difference. But because they are not connected in the same way, they're not aligned in the same way as a quantum instrument does, it doesn't suppress the noise quite as well. Here are the quantum instruments. This is our gravimeter. This is our gradiometer, so just a slightly taller sensor head. You see the people in there, so you can see how much bigger it is. This is our classical instrument. This flight case hosts all the electronics. You see it in action in a minute. This is just again to emphasize why a gradiometer has advantages, because all this common noise, what I call noise, other people might call it, they're really interested. That's their signal of interest, but it's not mine. But you can see that I can suppress it when I take the difference and I don't have to, it means it's much easier to correct for it and get a clean signal. So just to show you how slow a traditional instrument is. So this is still our CG5. This is along a railway survey, and it's mainly looking at the time, how long it takes. So we've done probably about 20 meters in this video. And it takes over 2 hours. A lot of standing around. For each point, you have to take a number of repeat measurements because it drifts over the time. There are issues with sensitivity, so you do quite a lot of repeat measurements. So this is the results that you get from that type of survey. So we have done a survey along a railway line. So this is our railway line, and you get a signal like this. And this is what you now have to interpret. And the interpretation is basically if you've got a low, gravitational low, it means there's some low density. If you have a gravitational high, there's some higher density. So we knew where this asset was. This is a drainage asset, culvert under the railway embankment. We knew where that was. And you can sort of see a low here, but that low is not that much different to this low. So you really need to know a bit. But the problem in apostrophes that we had here is that there was a feature here that nobody knew existed, and it was basically an underpassage or a tunnel which was filled in with loose material covered at the end, so you couldn't see it at the embankment, but it had a significant impact on your measurements. The one thing that we actually also looked at is can we use this technology to look at animal barrows? So badgers are a protected species, and if they are on your site, it's a problem because you have to rehouse them. So knowing where they are is actually quite important before you get on site. But we are now talking about a badger is maybe this in size. So the barrows are, I don't know, 150 millimeter in diameter. It's stretching the capability of a gravity sensor, but it's also stretching the ability of a GPR sensor. So the top is a GPR, very noisy. The bottom one is gravity. And again, there's a lot of information on this slide, but really what we are trying to show is that it's multiple sensing technologies that help. So here you can hardly tell that there's noise, but that could be just a variation of ground. Here you GPR possibly, but in combination with your microgravity, you probably could find, or you have more confidence in the results. This is the same idea. I realize I'm getting a bit tight for time, but here we have done earth resistivity and gravity, and it gives you the sort of same idea that combining two sensing technologies gives you a lot more confidence. Some of you may have seen that we've published a paper in Nature on our quantum technology work. This is where we had a multi-utility tunnel. Doesn't matter, it's a multi-utility tunnel. It's a big void in the ground, about 0.5 meter below the surface. We had our sensor on the top, and you get a picture like this, and you have to interpret this. But what we basically, this was the world first use of a quantum technology gravity gradiometer, which could actually detect a physical feature, a civil engineering related feature in the ground, and we successfully detected it. But it also shows you've got like an uncertainty profile. But it was really a significant achievement because normally these sensors are on optical tables in physics laboratories, so they are not out in the field. What's the application? Ultimately, we want to develop maps. We want to use it for gravity cartography. So you can really look at water monitoring. Can we look at aquifers? We look at tunnel monitoring, but also archaeology. There's also a big drive about navigation where you can't use GPS, so you're using map matching. So if somebody's into navigation, there's quite a lot of work we're doing here. There's actually, in terms of our quantum work, there's quite a bit of work in the medical field as well on the quantum magnetometer that we're using to replace maybe your CT scans, and you can do a lot of brain imagery. That's not my field of expertise. But just to mention that that might be something, I can certainly make the linkages that there's quite a lot of work in that area. So that work culminated in our Nature paper, which is again freely available. And you can see a lot more detail. But finally, to finish off here, I just want to talk about our large scale test facility, the National Buried Infrastructure Facility. Because it has twofold. It really gives us a large scale control test site to do a lot of our testing now. And it opened, as I said, last year, summer last year. So it's been open for not even 12 months yet, but close to. And this is really a unique facility. There's nothing else in the world where we can really do large scale testing. And the key is that we can do control tests. We can control the material. Normally we use a coarse grained material, so it's a sand filled. But also we can control obviously what we bury, where we bury. We can do lots of sensing technologies, both existing sensing technologies as well as novel new sensing technologies. We can also control our environment and our noise influences. Here's a picture of the facility. I'll just go through the images very quickly. This is in the center of the facility. You can just about see it here. It's what's called a movable floor. So the idea is that you can simulate ground movement. You can do that as a result of tunnel operation, but also as a result of slope stability issues or anything else, or leakage. So you can simulate ground movements. These are 50 actuators, and they can move up and down, and they can give you a travel of 300 millimeters, and that's how you can simulate ground movement. We would normally, so this is 25 meters, I should have probably said that, 25 meters by 10 meters by 5 meters deep, so really big. We would normally split it into 3/3. So here's 1/3, there would be another wall on this side, so you've got 1/3 here and then the middle bit to do experiments, but we can also use the full pit as well. It's got strong floor around it to do some more smaller scale tests. We have got a structural frame as well. You can see a visualization suite and meeting rooms, so we can actually do things. So you don't necessarily have to be in the country and be there to participate in the tests and to really see what we're doing. It's obviously, it's basically a construction site, so we've got quite a lot of plant. We've got offices for both our PhD students, our research fellows, but we also have knowledge transfer offices. So if you wanted to come over, if anybody wanted to come over for a period of time, we do have offices as well, because we do appreciate that the day job continues. We did do an experiment, a quantum experiment, where we added a pipe to the system. First of all, we had to close off the end bits because we didn't want soil to flow into the pipe, quite a large pipe, around 2 meters in diameter. We then filled the pit. We fill it in layers, 300 millimeter layers, very controlled conditions where we compact it very carefully. We use a nuclear density gauge to measure, which is there on that picture, which we use to measure the density and really giving you really accurate controlled conditions. This goes on. You can see we buried also a gym ball because we wanted a different target. Ultimately, all the way to the top. And as you can see, quite a lot of people were involved in the process. We then had our quantum technology sensor in the facility. So here you see the quantum technology a bit in a slightly different guise. So it's a bit further developed, so it looks slightly bit different than on the other pictures. So as you can see, this is all part of our quantum technology hub that we have at Birmingham. And I think in the introduction, it was said that I lead the geophysics aspect, so the civil engineering aspect. So what's really nice about the quantum technology work is that it's always been a collaboration between our physics team and our engineering team. And I think that's what allowed us to advance it quite significantly. So the other thing with the quantum sensor, what I should say, I said the classical sensor is a stationary sensor. The quantum sensor will have the ability to be ultimately mobile because you can sample much quicker. And that will be a significant advantage because one of the problems with the existing sensor is just the time it takes to do the surveys. So coming to my final slide, as a summary on what this talk was all about, it felt a bit like a whirlwind about some of the research I've done over the last 10, 15 years. So I'm more than happy to discuss anything in more detail if you want more information. But in summary, basically that the subsurface and the underground space is a really challenging environment. But it's also an opportunistic environment. And what I mean by that is we obviously bury quite a lot of features in the ground. We have buried assets, so pipes, cables, tunnels, basements, underground storage, shopping malls. And the problem is that the ground really influences how things behave. And one of the problems is that we don't really have a lot of sensors in the ground, and that makes it quite difficult to manage it from an asset management viewpoint. So we normally use a sort of stochastic approach to predict the behavior of our subsurface assets, and that's not really a good way of moving forwards. The other thing is, with the onset of climate change, we're probably going to use our underground space more and more as well. And it allows us to put things in the ground that we don't want to see above ground and free up surface space to make it greener. Industry clearly uses a suite of sensing technologies, often geophysical sensing technologies from the surface, but we can get more information out of the data that industry regularly does. And I think we can support industry in utilizing the data much more. We can't just rest on our laurels with existing sensing technologies that do have limitations. So we do have to look at new sensing technologies. And for example, quantum technology sensors are one of the suites of sensors that you could use to look through the ground. But really what we need to do is we need to have a much better understanding of the ground to make excavation safer, but also to allow us to use the underground space more efficiently in the future. And with that, I would like to finish and say a big thank you again for allowing me to speak. And hopefully I haven't gone over too much, and any time for question and answers.
All right. Thank you very much, Prof. Nicole, for the knowledge, your past research on the topic of infrastructure monitoring. As the faculty of the Infrastructure Planning Engineering Master Program, I think these area of topics that rarely discussed, especially in our university. And I think hopefully that from your presentation, we can have more discourse regarding this infrastructure monitoring. So to briefly sum up what those underground utilities are quite often, be it in the UK or Indonesia, and I think it is quite crucial to emphasize how much it is not only like financially costly to repair or to do this monitoring, especially when you are excavating the ground in order to monitor these utilities, but also it is time consuming because, like, you know, if you have to wait for this to end, then I think, yeah, as what you said, that we are dealing with congestion, we are dealing with many disruptions, especially on the over the ground. Prof. Nicole also explained various monitoring techniques and sensing technologies, from a relative pressure sensor to ground penetrating radar, geophysical technologies, and to so I think from the talk we can really appreciate how much field of science involves in your work, because it is not only civil engineer doing this. I think you also have like electrical background also involved. I think that we can see how the disciplinary the work in regards to this infrastructure monitoring. So this is not only work engineer. Yes, I think we have had one question from Mrs. Effie. Mrs. Effie, are you here?
Yeah.
All right.
Hi,
Yeah.
Akbar.
Yeah.
Thank you
Hello.
for giving me the chance. Hi, Prof. Nicole. Nice to see you.
Yeah, nice to see you too.
um, first time I see this flyer, and I'm interesting for this topic that I'm working with. I also working in a sensor digital monitoring for infrastructure, but on horizontally, I'm mapping. I make forecasting for the traffic for vehicle, high vehicle, and medium vehicle. But one thing that the more challenging for me to figure out when I started to begin my researches, many people ask me, how do you believe that the artificial intelligence can help you in the assets monitoring or infrastructure monitoring process? Is this real, or maybe like you just maybe make a joke? Then I just answer that the artificial intelligence is not just a single variable that we include and a single way to processing the data. And we are focusing on what we want to figure out at the end of research. And what I interesting during your explanations that you make a challenge like obstacles like a noise being one variable that you have to put in the measurement. That's why in my I'm develop the artificial intelligence working on how to focus the horizontal traffic management in Makassar, and now it has been 5 months since February 2022, and yeah, uh, actually it's not all is a success, but I face many failed situation, but it doesn't make me like I need to give up for these things. One question I wanted to ask you, which is more important for you, Prof. Nicole, proactive identifications of slope instability or reactive identification of slope stability? That you are working vertically, right, on the infrastructure. You want to measure, you want to make a mapping for the ground absorption and density, durability, and any other else. So the big question for me, because it also influenced to my sensing. I also working on a sensing monitoring for the traffic. Does proactive or reactive identification for the slope instability for you? Which one is more important in a sensing quantum technique of a sensor sensing method? Thank you.
All right. Thank you very much for the
Thank
question.
you.
Yeah, Prof. Nicole, do you get the question?
I think so. I think it's quite difficult to answer. So what I'm really after is active monitoring is what
Okay.
I want. Because what I want is active asset management. I don't want reactive asset management.
Okay.
Reactive
So-
is what we currently do. We wait for a problem to occur and then we fix the problem. We want to be and that's often expensive. So I think Mohammed mentioned the expenses, the costs, and the problem is when I can see something, because most of the time I can't see my problems because it's out of sight, out of mind. It's in the ground, I can't see it. The time I normally see this is when there's a failure at ground surface. So either when there's water coming out, when I have a leak, or for example, when I have a sinkhole, because the road has collapsed because soil has been washed away. At that point, the remedial work is very expensive because it's quite a big job. If I could have known about for example, a leak early on, I could have probably gone in with keyhole surgery. So just drilled a little hole with the vacuum excavator and fixed it. So really what I ultimately strive to is active real-time measurements to allow me active asset management.
Okay.
I'm not saying we are there yet, because the problem really for us is we do not have sensors in the ground. In most places, there aren't any sensors. So we tend to do things a lot more reactive, because you go to a site and you do a survey, and you then, what we at the most do at the moment, we do what's called a time lapse. So we do it 1 year, then we tend to go back 1, 2, 3 years later and see if there's a change. But again, the time frame is really large. Okay. So this is a lot of the work we want to do, is try to have sensors in the ground. A lot of the changes don't happen very quickly. So I don't need a measurement. I don't need a measurement every second. I don't need a measurement every minute. What I'm interested in is maybe a measurement once a day, once a week. In most cases, is probably good enough. But we are just not there yet. So even with a quantum sensor, the way it's at the moment, in the near future, it'll be a surface sensing methodology, method that you do 1 day, 1 week, then you take the sensor away, and you may do it again as a time lapse a bit later. But what we really want to get to is incorporated sensors. So one of the projects I didn't show in my presentation because it was just getting a bit big. We're doing something where we have sensors in pipes. We do swarms of robots in pipes that live in the pipe and give you some information about the condition of the pipe, and ultimately also act as repair bots, so they can repair a defect in the pipe. If we really get this to work, so this is another 2 years project at the moment, it's an ongoing research project. If we really get that to work, that would make a significant difference, because we always have sensors in the system. But ideally it's active, is the short answer.
Akbar, may I add some question again?
Yeah.
One more question, Prof.
Sure, yeah.
Thank you, Pak Akbar. I'm really interesting for this quantum sensing methodology, because it's really new for Indonesia, right, Pak Akbar? Yeah.
Yeah.
I'm a lecturer in transportation engineering in graduate school, and it really works. How we forecast, how we map the traffic, especially for the high vehicle, because we are now developing the rail transportation, right, for Makassar to Parepare. And so far, load sensing is providing more proactive identifications of stability, because of the parameters that we include in our research is really easy to measure. It also generating like alerts for us as a community, that we need to be more respect, to research, because someday I put I put our tools in between Makassar to Maros, and then tomorrow our tools will be disappear. I don't know who stole our tools. That's the very challenging very challenging day for us. So we need to install again new tools and put again in a different places. Last question, maybe Prof. Nicole, before I leave this Zoom. I'm curious about the level of implementation, because sensing, that it will take cost and time, as you mentioned before. How many how many infrastructure, or maybe ground, because there are many applications, artificial intelligence like HECRAS, Plaxis, also include sensor inside to make a mapping about the ground, about absorption, about the type of land. Pak Akbar is an expert on Plaxis, I think, application. I'm curious about the level of implementation of your tool.
Okay. I've used it before.
That's the final question for me, Prof. Thank you for the chance, Pak Akbar. I really interested for this.
So again, I would like to give you a really straightforward answer, but again, it's not that straightforward. So we, as an academic, you generally get as far as proof of concept, but the proof of concept can be quite what we call Heath Robinson. I don't know whether you've heard of this term, but it's basically lots of cables, lots of wires. Yeah. It's not ruggedized. It's not really a practical sensor you can use in the field. So we really shielded. We sometimes have we even have a PC and a laptop and,
really
complicated. And things on the side. And it's not something you could really implement. But the problem is that our funding is only allowing us to go as far on our what's called TRL, technology readiness levels. So really, it's easy for us to get funding for the low end, where we really do prototypes, proof of concept, but a prototype is not designed in a way that industry needs. A prototype. So our quantum sensor as it stands at the moment still needs someone with a physics degree to operate it. I can't operate it. It still needs my colleagues from physics. We're working on it. And what's working for us is this collaboration on this particular example, because we can say, this is not something an engineer could do, or this is not something we would operate on site. And so we are pushing it in that direction, but it is quite challenging. Yeah, it's a bit easier with some of the industry projects where a lot of the aspects we're rolling out in industry are actually not the sensing technologies, it's the processing, it's algorithms, it's software, it's because they can implement that very quickly. So we have developed codes and models with industry, for industry that they are using now. That's a direct output of our research. But it's not the all singing, all dancing sensor. There's still always a lot more work. And this is almost where my role as head of enterprise engagement and impact comes in for the school, where I'm really trying to now make this step. But it's quite hard to get this extra funding at times to read. So we're trying to bring industry in. So we're talking to the likes of Dyson, you know, the ones who make the vacuum cleaner, because they like entrepreneurs who have lots of funding to put in funding in, and we are talking a lot more about spin out companies. So for the quantum sensor, we have a spin out company called Delta G that hopefully will ultimately make these sensors and sell these.
Yeah, commercialization is very hard, very difficult. Maybe I can invite you to collaborate with me in my research. I'm doing on horizontal, you are doing on vertical infrastructure, right? So we can collaborate, I think.
Sounds like a plan.
Thank you, Pakbar. Thank you, Prof. Budu as my dean. Thank you, Prof. Nicole, for giving us a very interesting topic, very interesting research. Yeah. Thank you very much, Pakbar. I see you again, Prof. Nicole. Thank you.
Thank you.
Nice to meet you.
Yeah, thank you, Ms. Effie. Yeah, thank you, Prof. Nicole, for the response. I think we can move on to the next question. Do we have anyone who have question to Prof. Nicole in the Zoom? You can just raise your hand or just unmute your mic. If you're not comfortable with English, you can just ask the question in Bahasa, then I can translate it for you. Anyone in the Zoom? Do you have any question? I actually have one question. Okay. Yeah. Mr. Widodo.
Hello, Mr. Akbar, can you hear me? Hello.
Unmute your mic. Yeah.
Yeah, I can hear you. So.
Good afternoon, Professor Nicole. Can you hear me?
Yes.
Okay. Mr. Moderator, Pak Akbar, thank you very much for the chance. And Professor Nicole, thank you very much for your nice presentation. Of course, I would like to say I'm happy to see you in our webinar. Before I ask something, but my first question, is it true that you are graduate from Hannover University, Germany?
Yes. Yes.
And I'm sure you can speak German very well.
I can. I hope. It's my mother tongue, so I am German.
Okay. Therefore, I would like to speak German. Before a very long time, I not could speak German.
That's fine with me.
Ich heiße
Guten Tag.
Widodo. I'm graduate from Frankfurt University for my PhD program. Yeah, but my German is better if compared to my English actually. But the other participant cannot speak Germany. Unfortunately, I have to speak English. But
Wir können Deutsch sprechen und ich übersetze.
Genau. Sie können übersetzen, ja. Aber ich habe Angst, wenn die Kollegen kann nicht verstehen.
He says he's scared if the colleagues can't understand him.
Yeah, yeah. Nice to meet you, yeah. By the way, I have some questions. For the first questions, is it possible with this technology, based on your explanation, to identify the kind of material like soil? Because based on your presentation, you mentioned at the slide that how to identify something at the ground, topsoil, subsoil, and so on. But actually, yeah, I come from mining engineering department, Hasanuddin University. Therefore, I think it is important for me to looking for more information from you. The first question, it is possible to identify the type of lithology like sand and also clay and so on. And the second question,
can I just answer one question at a time? I will have forgotten the second question, the first question otherwise.
Yeah, one at a time. The first question first, then you can ask the next question. Yeah.
So
we have to answer one by one, yeah?
One by one, please. So you can to a certain degree. So what a gravity sensor does, it measures changes in density, but the problem is that it gives you an average value with depth. So it will merge the different layers. What it does identify, though, coming from your mineral aspect, so gravity sensors, not quantum, but gravity sensors are used for mineral deposits, are used for oil reservoirs. So they can, in theory, measure down to several kilometers in depth. They are really used a lot in the mining industry. They are also used, big companies, oil companies and military use it on planes. So they fly it over to cover a large area. So that's, but the deeper you go, the bigger the feature of interest has to be. So if you want to measure something 800 meters, a kilometer below the surface, you have to have a very large feature of interest, which a oil field or mineral reservoir would be. But as a civil engineering, I'm probably more interested in the top 50 meters or maybe even the top 20 meters. And it's a different approach, but you can use it. Can you really identify the layers? You may be better with a different sensing technology. If you're talking at the top 10 meters, 20 meters, earth resistivity would be a lot better, but it's quite a cumbersome technology, because you put the probes in the ground and you have to change the separation of the probes to get deeper the further apart they are. So I'm out of the picture now, but the further apart they are getting deeper into the ground. So it is, so again, there are sensing technologies, and what we're using our gravity sensor for, interesting enough, is carbon sequestration. I don't know whether that's something you've looked at, but as you know, we need to store carbon with the onset of climate change. So we're pumping carbon into the ground. It will displace the water in the ground and fill the voids. And we think you can measure with a gravity sensor, you can measure how far this carbon has penetrated into the different layers. So again, you can do something, but if you're just wanting the clear separation between topsoil, subsoil, it is difficult.
Okay. Alles klar.
Okay. Next question.
Everything is clear. Alles klar.
Alles klar. Super.
Yeah. Danke schön für die erste Frage. Thank you for the first questions.
Kein Problem. No problem.
Mr. Moderator Pak Akbar, I'm sorry. Yeah, I have to mix our language today. The German say Denglish, Deutsch und English. Yeah, the language
No
mix
problem.
together. German and English, Denglish. Okay, the second question, is there any information for the cost, especially for this technology? Maybe in UK, this is low cost, but for us in Indonesia, this is high cost or expensive because we have different currency. And what is important, what I would like to know is the cost of this technology.
I assume you're referring to the quantum sensor as opposed to any other technology?
Yes, yes.
So again, these questions are all challenging. They're all really good questions, but they're no easy answer. We are still at the research stage. So if you talk about all the research money that goes into one of these sensors, it's probably, it's not at a price point where industry, even in the UK, would take it up. You're basically still talking of over £1 million. This is not what we would want this is not where we aim for. So if you've used a ground penetrating radar or you've come across these, they are between 10 and 30,000 pounds. So probably, I think it's almost the same in US dollars. So 10 to 30,000 US dollars. And that's the sort of price point where we want to be. The classical instrument, the mass on a spring gravity instrument, costs, if you buy it in Canada at the moment, it costs around $120,000. But the way industry uses it, they use it as a higher instrument, and we foresee that maybe the quantum instrument will also be initially a higher instrument. So there are a few companies in the UK who own this instrument, but they hire it out to industry and hire it out to academia. And then the charge is a daily rent. So we foresee that maybe initially our quantum sensor will be a similar business model, so that a company buys them for in the order maybe 120, 150,000 pounds, dollars, and then you rent it on a daily basis. But we do have, sort of ongoing work. We've got a international collaborative network, especially on the quantum side, where we are trying to look at different application areas with international partners. I can't quite remember which country is involved from the onset, but there may be, if this is something you're particularly interested in. I'm co-lead of this international collaboration. It's only just started. We only just won the funding in around Easter time. So I'm sure we can, there will be webinars and there will be workshops, and you can actually come here and use the sensing technology as well. So there are opportunities to collaborate without having to buy 1.5 million worth of equipment.
Thank you for your information, Professor Nicole. And the last question?
Yeah, geschehen.
One more question, yeah? Pak Akbar, sorry.
Yeah, okay.
For this technology, it is possible to working at the underwater.
So one of the research areas we're looking at is putting it on autonomous underwater vehicles. Yeah. So you actually have it on small subs. That's the plan.
Yeah, actually, I just want to asking, it is possible to working at the lake or at the sea, if possible.
So at the moment, as I think my answer before, with all the cables sticking out or so, at the moment it's definitely not waterproof. It's not even rainproof.
Yes, yes.
That's what I'm saying. We envisage that it would be on a little submarine, so not a big submarine. These autonomous vehicles, because one of the application area, and I mentioned navigation very briefly in one of the slides, is to do this map matching because one of the problems you have underwater is your navigation, because you can't get GPS coordinates because you're below the surface. And therefore, the idea is that you create a gravity map, and next time you come to this location, you can match where you are with in relation to your existing map. So that's some work that we're doing. So, but at the moment, it's definitely not waterproof.
Waterproof, yeah. Okay. Thank you. Everything is clear. Yeah? CNC, clean and clear now. Yeah.
Super.
Okay, thank you very much for your nice information, of course, and your nice presentation. Have a nice day in Birmingham.
Thank
Ik
you.
bedank u voor Ihre Information und ich freue mich, mit Ihnen kennenzulernen.
Ja, gern geschehen.
Thank you very much. Danke schön.
Vielen Dank. Vielen Dank.
Gut gemacht. Vielen Dank, Professor Nicole. Thank you, Pak Akbar. Thank you very much, Pak Akbar, for the chance for me to discuss something with Professor Nicole. Thank you very much.
All right. Yeah, thank you very much, Dr. Widodo, for the question, and Prof. Nicole for responding to the question. Right, we can move on to the next question. I think we can still accommodate one more question. Do we have any question from the audience in the Zoom? Yeah, I think, yeah, do we still have one more from the audience? If no, then I think we can end this session by the last question from me. Wait a second. Yeah, so yeah, I've done or water retaining infrastructure. So I'm wondering if the sensing technology that you have just explained would be able to sense or detect the defects or cracks that are formed inside the dam. So the issues that I'm talking about is the detection of piping erosion or backward erosion. I think you are quite familiar with these terms. I think the problem is most of the time we can only identify there is a piping erosion developing in the dam after the drain is detected at the downstream side of the dam, which at the moment, at that moment, the eroded hole has been fully formed. I think, well, ideally, we would like to detect the crack as early as possible. What we are doing right now, we are inclining to just follow the design standards. They are more prescriptive. So in order to ensure that we can prevent or we can minimize the potential damage, but this is not necessarily like preventing the damage altogether. So I think I know there was one experimental test using resistivity sensor research in the University of Birmingham. When I did my PhD, I almost did my PhD on the identifying the internal erosion using the sensors, but I gave up because I think this is quite hard to figure out where the direction goes. So I was just doing the geomaterial investigation on the material used for the dams. But my question is, do you have any ideas how this would be possible with the sensing technology? I mean, to detect the piping erosion or internal erosion at the moment? Yeah.
Yes, sorry, I just had to think. Yes, one of these, so there was one slide I moved over very quickly because I realized I was getting tight with time. And this was where we had earth resistivity as well as gravity measurements. And this was along a embankment, a canal, where we looked at leakage through the canal. So again, it's a question of size and depth. So if you've got something really small, but really deep, we can't detect it.
Okay.
If you've got something that is small, but quite close to the surface, we can start detecting it as it occurs, but a gravity measurement measures changes in density.
Okay.
So what I need is I have to have compacted soil, or soil, doesn't have to be compacted, but soil. And then I have to have something different. So that could be a water-filled area, or even better would be air-filled, because air-filled is better in terms of the bigger density difference between soil and air compared to soil and water.
Okay.
So therefore I can then detect it. But as I said, any gravity sensor works, so it's like a cone shape. So where at the top of my fingers is where your ground surface is. And the further down you go, the larger the feature has to be. So if I, as I said, if you're asking me, can I detect something that's 3 meters below the ground surface? I tell you yes, but it then has to be half a meter in diameter.
All right.
And ideally air-filled, because that gives me the biggest contrast.
Okay. Okay. So there should be a difference of density. Is that what you're suggesting? All right. Okay.
It's a density change is what my gravity signal picks up.
All right. Okay. Okay. Understood. Understood. Okay. Thank you very much for responding to my question, because I'm asking this question because I attended one of the webinars probably 2 months ago, and the answer was basically we need to wait until the when we can monitor the internal erosion is when when the erosion happens, which I think that this is not ideal condition. But I think what you have just explained just give me some ideas of how we can approach this monitoring for the dams for the potential internal erosion. Right. Thank you very much for the answers. I think we are almost reaching the time, so I think I will wrap up this question and answer session. If the audience have any question to Prof. Nicole, I think you have put your email in your slides. Do you put your email there? I mean, anyway.
I should have done, but I don't think I did put my email address in the slides. Right. I can put it quickly in the chat, but also people can contact you if they have any more questions.
Yeah. All right. Yeah, that will be fine. Yeah. Anyone, if you have any question to Prof. Nicole, you can just see in the chat box. Prof. Nicole just drop her email there. You can just contact her if you have any question regarding the topic that she has just explained. Right. So thank you very much, Prof. Nicole, for the presentation, for your very useful insights throughout this question and answer session. Is there any way we can have an access to your slides, or wait, do we record this webinar, Bu Israini?
Yes, we are.
Oh yeah, all right, okay. I think you don't need to share your slide because we have the recorded webinar anyway. Yeah, so thank you very much for the talks. Then I would like to give back the floor to the Master of Ceremony.
All right. Thank you very much, Professor Nicole Meje and Dr. Muhammad Akbar Walina for valuable knowledge and time. And as our appreciation, the Vice Rector Hasanuddin University made this the certificate to Professor Nicole Meje. Please, Mr. Amri, could you show it? All right. Yes, this is the appreciation from the Vice Rector Hasanuddin University for Professor Nicole Meje for sharing her valuable knowledge to our students and lecture in University Hasanuddin. And don't be worried, we will send the certificate by email as well with Dr. Muhammad Akbar as well. And then, thank you very much. All right, ladies and gentlemen, before we officially close our webinar, we want all the participants to open your camera because we want to take photo with our distinguished speaker, Professor Nicole Meje. And I will count in 10 seconds, so please open your camera, everybody. All right. here we have 2 slides. So I will count it. All right. Okay. 1, 2, 3. Smile. And the second slide. 1, 2, 3. Smile. All right, everything is awesome today. We finally come to the end of today's agenda, and let us close the webinar by reciting Alhamdulillah. Alhamdulillah Rabbil Alamin. And those are the agendas we have presented to you all this afternoon, I'm sorry. We hope you learned something, and thank you so much for your attention. See you on the next occasion. Wassalamualaikum warahmatullahi wabarakatuh. Maybe Professor Nicole, you want to say something to our to the last speech, maybe?
Yeah, I think it just remains for me to say thanks ever so much for giving me this opportunity, and it was a really fantastic discussion and lots of challenging questions, so this is really, really good. I think there's lots of potential in terms of sensing technologies in general, so I spoke specifically about buried infrastructure, but it could be much wider, general infrastructure, and I think there may be, I know there are applications in other fields as well. So all I can say is thanks ever so much for giving me this opportunity, and hopefully I might meet some of you in person. Either maybe one day I might come to Indonesia, or we see each other at conferences. But also you're welcome in the UK as well. So thanks ever so much again to everybody.
Yeah, thank you very much, Prof. Nicole.
Thank you very much. Prof. Budu, if you want to say something.
Okay, I just say to thank you very much for Nicole meet you, Professor. Thank you so much.
All right, thank you very much, everybody. See you on the next occasion. Bye-bye.
Bye.
Bye-bye, Prof.
Bye-bye.
Nicole.
Bye.
Thank you very much.
Bye, thank you.
Thank you,
Thank
Prof.
you.
Budu, Pak Akbar.